Good morning, ladies and gentlemen, and welcome to this lesson and lecture on the antipsychotic drugs that we are currently busy with this week. So the antipsychotic drugs, the first antipsychotic drug that was identified or discovered was chlorpromazine, and it was discovered in the 1950s. Now, with this presentation, I'm just going to go briefly through the different sections. I will stop and provide some additional information on those sections that I think is important for the exams and where I can give you some pointers and tips on. But on the rest, I'm just briefly going to go through this. Make sure that you do read through the introduction and the case of chlorpromazine and how it was discovered. We know that there are different types of psychosis, like, for instance, schizophrenia. We can see depression, mania as well, these affective disorders. And sometimes you can even get psychosis or these type of disorders by head injury or alcoholism or other kinds of organic disease. So what were the treatments before we had drugs? Well, you can see here that patients were kept isolated, shock treatment, some cases even insulin shock therapy, or they were institutionalized. So luckily in modern day pharmacology and modern day medicine, we have drugs that can work against these different type of psychotic disorders. So if we look at the different classifications of the antipsychotics, for instance, you get the anti-schizophrenic drugs, also known as antipsychotics. You have anti-manic drugs, antidepressant, and anxiolytics that can form part within this drug class. So pharmacologically, these compounds are characterized as dopamine receptor antagonists. They're mainly working on the D2 receptor, where they block the D2 receptor. Please make sure to watch the introductory video on the pharmacology. The pharmacology for this part and for these drugs are quite important. Something else to note is that although these compounds bind to the D2 receptor and block this D2 receptor, it can also have an effect on other receptor systems within the brain as well, and particularly the serotonin receptors. And I'll show you some more of that as we go through the slides. You can also see the antipsychotic drugs. The antipsychotic drugs do not cure psychosis or schizophrenia. They can only mitigate or eliminate some of the signs and symptoms associated with psychotic disorders. So this is very important. It is not a cure. It is very effective medicine, but if you stop taking the medicine, your psychotic disorder will return. So it is not a cure. It basically just elevates certain neurotransmitters, like in this case, it elevates the levels of dopamine in the central nervous system. So for schizophrenia specifically, there are two different types of symptoms, like positive symptoms and negative symptoms that they use to diagnose a patient suffering from schizophrenia. And about 1% of the world's population could suffer from schizophrenia, and there is a strong but not invariable hereditary component. The main thing, the main neurotransmitter that is responsible for the development of psychosis and schizophrenia in this case is dopamine and dopamine overactivity. And this is known as the dopamine hypothesis. So if we look at the dopamine hypothesis, this hypothesis suggests that excessive dopamine activity causes schizophrenia and other psychotic disorders. And you can see here that they've given us some reasons, like, for instance, certain drugs that increase dopamine activity can aggravate some existing schizophrenic symptoms. Traditional antipsychotic drugs block the D2 receptor. So by blocking the D2 receptor, lowering down dopamine levels, it seems as though that this works. They also saw in post-mortem brains that there was an increase in dopamine receptor density and overactivity. And even some of the dopamine metabolites, like, for instance, homovolinic acid, is found in patients who suffer from psychosis. So because of this, this is the dopamine hypothesis, where they can see that if you decrease, my apologies, when you increase dopamine activity, then or dopamine levels in the brain, then it leads to then it could lead to the psychotic disorder. So please make sure to go through the dopamine hypothesis. It is quite important. for you to know what the dopamine hypothesis is and how it fits into these psychotic disorders and the drugs that we are currently using. Please make sure to put in some effort into this. It may be a nice exam or test question to ask. Then there's some further information, basically what I've just spoken about, the mechanism of action, the dopaminergic overactivity, and then some dopamine antagonists or agonists that can exacerbate schizophrenia if the dopamine levels get too high. There are two main categories of the antipsychotic drugs, mainly the typical antipsychotics as well as the atypical antipsychotics. So the typical antipsychotics are all older antipsychotic agents, like, for instance, haloperidol, chlorpromazine, and fluphenazine. So these are the different typical antipsychotics, and they mainly work by blocking the D2, the dopamine D2 receptor. Then we get newer, more modern day antipsychotics known as the atypical antipsychotics. And the atypical antipsychotics can block the dopamine receptor, but they also have effects on glutaminergic receptors and serotonin receptors as well. So the atypical antipsychotics are non-selective drugs. They can work on numerous different targets that are associated with psychosis. It is a little bit more difficult for the atypical antipsychotics to develop structure-activity relationships because they can work on different targets at the same time. The atypical antipsychotics can also be referred to as multifunctional neuroleptic drugs or multifunctional antipsychotic drugs. Multifunctional meaning that they have different functions, they can work on different receptors at the same time. Also, the atypical antipsychotics are also less prone to adverse effects and certain side effects associated with the antipsychotic drugs. And the reason for that is because they don't just work on a single receptor target. So they're not potent just for a single receptor. They work on numerous receptors in a moderate potency. And it seems as though that has led to a slight decrease, or not a slight decrease, but a decrease in some of the side effects associated with the typical antipsychotics. So let's look at some typical antipsychotics and some examples. So the one example is chlorpromazine, our very first neuroleptic drug or antipsychotic drug that was discovered. You can see the structure of the phenothiazine or chlorpromazine here. The chlorpromazines fall within the drug class of the phenothiazines. And the phenothiazines, as I've already said, it's a typical antipsychotic and it blocks D2 receptors and in that way decreases the dopamine levels. And we know that according to the dopamine hypothesis, overactivity of dopamine in the brain leads to psychosis. If we look at some of the structural properties of the phenothiazines, now this also makes up the pharmacophore of the phenothiazines. You have the phenothiazine heterocycle meaning that it's more than one aromatic group within the functional moiety. So it's a heterocycle made out of two ring systems, contains a sulfur and a tertiary nitrogen, and at the 2 position, there is the possibility of adding an electron withdrawing group. It also has an alkyl connector. This alkyl connector always needs to be a 3-carbon alkyl connector. If this now changes, if you lengthen this chain or make it shorter, then you lose the pharmacological activity or the antipsychotic pharmacological activity. We also require a tertiary amine, and that tertiary amine is important for biological activity. If you change it to a secondary or a primary amine, you lose the biological activity of the phenothiazines. So this basically is the pharmacophore of the phenothiazine drugs. I would say that this X group here at position number 2, where you can add electron withdrawing groups, that is basically our oxyphoric group, where they have done quite a few structural modifications using that X group. And this tertiary amine, you'll see it's connected to a R2 group. Now, this R2 group is different type of ring chain transformations, where you can also then do different substitutions because that R2 is an oxyphoric group. I will show you some R2 substitutions just now. So further structural properties of the phenothiazines, they are unsuitable for oral dosage forms because they have a very, very high degree of lipophilicity. So this is necessary for the drug to be absorbed across the blood-brain barrier and work on the central nervous system. Remember, psychosis affects the brain. So we need these drugs to cross the blood-brain barrier, be lipophilic enough and act in the central nervous system. But these drugs are too lipophilic to be absorbed from the gastrointestinal tract because you need some degree of water solubility for a drug to be absorbed and cross the biological membranes of the GIT. So what the researchers then have done, and this is a general process that's been used for a lot of medicines, in which you can increase the water solubility of the drug. So for instance here, you would use the phenothiazine, it has this tertiary amine, you would then treat it with an acid, an organic acid, like for instance, hydrochloric acid, to form a water-soluble salt. So here you can see what happens is that HCl then reacts with the tertiary amine, making it a salt form. If you go into the pharmacy as well, you will see that the majority of drugs, if you look at the API that's in it, will be, for instance, phenothiazine HCl or finasteride HCl or amantadine NaHCO3. So that is basically then that NaHCO3 or the HCl indicates that it's a salt form of this drug. And the salt form of the drug increases the water solubility. So you must remember, now you take the drug, it goes into your gastrointestinal tract, it's water soluble enough to dissolve in your gastrointestinal tract. And then what happens is this hydrochloric salt then converts back to the tertiary amine once it's been absorbed from the gastrointestinal tract, and it reverts back, and then it's lipophilic enough again to cross the blood-brain barrier. So salt formation is very common in drug design and discovery to increase water solubility, to make the formulation process a little bit easier as well, because you have more water-soluble drug. And this drug can then be absorbed in the gastrointestinal tract, converts back to the primary drug, and then it crosses the blood-brain barrier. The inverse can also be done. Sometimes with these antipsychotic drugs or these phenothiazines, they are lipophilic, but we will then sometimes want to increase the lipophilicity even more. So for instance here, fluphenazine. Fluphenazine is a drug that can be used as a oral dosage form 3 times daily or 4 times daily. This drug is lipophilic enough to cross the blood-brain barrier, and they also develop the salt form of that on this tertiary amine to make it water-soluble enough to be absorbed from the GIT. But now, the problem with this is, now think about a patient who suffers from psychosis. That patient will forget to take their medicine 3 times daily or 4 times daily. Patient compliance is not good with a patient who suffers from these type of disorders. So what researchers then came up with is to make an intermuscular depot drug, so a depot injection. So basically a depot injection is where you inject it directly into the muscle. That drug is then in an oil form. It sits there as a bolus in your muscle, and then there's a very, very slow release of the drug over time. So what they did here is you will see that fluphenazine has this free hydroxyl group. Now, we know from prodrugs that if there's a free hydroxyl group, you can conjugate it to a carboxylic acid to make an ester. And this is what they did with fluphenazine. You can see with fluphenazine, they've added 2 different ester type moieties on that hydroxyl group. The one is an enanthate, which is a 5-carbon spacer. So that's that CH2, that N group here stands for 5 carbons. So it's a 5-carbon chain, and a decanoate, that is an 8-carbon chain. So what they did here is this ester or this intermuscular drug now will sit in your muscle, and slowly this ester will then be converted back into fluphenazine as it then gets released from your muscle very, very slowly. It's a slow process. And what you can see here is that the enanthate, because it's more lipophilic and because it's the ester that can now be slowly converted by esterase into the fluphenazine parent drug, it takes about 1 to 2 weeks. So the drug is then effective for about 1 to 2 weeks. Fluphenazine decanoate, if that even has more carbons, it's more lipophilic, and it will even stay in the muscle for longer and release slowly over time. You can see this drug then only needs to be taken every 2 to 3 weeks. So even though the fluphenazine enanthate and decanoate are intermuscular depot injections, they can then be used for long-acting treatment of psychosis. So this is a strategy that has been used, and the drug fluphenazine enanthate and decanoate, that are on the market, And it's much better for patient compliance because the patient just has to go to the clinic every 2 to 3 weeks, and then their psychosis is under control. Then if we look at some more structured activity relationships, there needs to be an electron withdrawing group in position number 2. There needs to be a 3-carbon spacer. That 3-carbon spacer, if it changes to a 2-carbon spacer, you lose the anti-dopaminergic or antipsychotic effects as shown here. If it's a 2-carbon spacer, then as I said, then it leads to a reduction of anti-dopaminergic effects, and it converts over to antihistaminic effects. So remember, this is the case of homologation. You can see here just that simple structural modification can change the pharmacological activity of the drug quite significantly. And then we also need that basic nitrogen. As we previously said, that basic nitrogen is also important for salt formation. The tertiary amines are the ones that are preferred. So you need a tertiary amine. If you have secondary or primary amines, then it decreases the activity. The side chain, like I said, that side chain needs to be a 3-carbon spacer, but also that side chain on this position with the tertiary nitrogen, you can see that there's a few ring chain transformations. As I said, at this basic nitrogen on those R2 positions, that is an oxyphoric group. And you can see here we have the different types of phenothiazines where they've used that oxyphoric group to do some ring chain transformation and change the activity of the phenothiazines. There are 3 types, like the aliphatic phenothiazines, because it just has this aliphatic chain. The piperazine phenothiazines. Piperazine is this moiety here. It's a cyclic moiety having 6 atoms in the ring system with a nitrogen, 1 nitrogen. So that's then a piperazine. And this one on this side is also a piperazine. You can see we've just shifted the nitrogen into the 2 position, but it's still 6 atoms. We have 1 amine in it, so it's a piperidine. And then we also have the piperazine phenothiazines, and the piperazine phenothiazines is just we have 2 nitrogens within that ring system. I'll show you now what the effects are of these different ring chain transformations. So these ring chain transformations causes differences in these drugs with their antipsychotic activity, the frequency of seeing extrapyramidal side effects like Parkinsonian-like side effects, sedation, and hypotension. And you can clearly see if we just go through the EPS frequency, you can see that the piperazines, they are very potent drugs. So there's a possibility of then showing Parkinsonian-like symptoms. The piperazines are not as potent or show as many EPS effects as the piperazines, and the aliphatics has the less potential compared to the piperazines to the piperidines to showing EPS symptoms. So EPS, Parkinsonian-like symptoms, remember these drugs lead to a decrease in dopamine levels in the brain. We know that Parkinson's disease is also associated with dopamine, and it's associated with a decrease in dopamine in the brain. So what sometimes happens with the phenothiazine drugs, when you decrease the dopamine too much, then it leads to some side effects that are like Parkinsonian-like side effects. So please make sure that especially this slide and the ring chain transformations that you see here, make note of this, study this for the tests and exams. This is a very nice question to ask. Even we can ask you sedation, which of the different type of phenothiazine subclasses will have the highest degree of sedation. You look at this table and you can see that the aliphatics and the piperidines have similar levels of sedative properties. So both this one and these will have similar types of sedation, but the piperazines has the lowest degree of sedation, but unfortunately it has the highest degree of EPS activity. So please make sure that you go through this slide and my notes and make sure that you understand it and be prepared for the exam. Here I've just shown you some examples of therapeutic phenothiazines. Just take note of this. You can also see some of the side effects associated with these drugs. Please take note. Then we also have some other typical antipsychotics, like for instance the thioxanthenes. Now, the only difference between the thioxanthenes and that of the phenothiazines is that the tertiary amine has just been replaced by a double bond. Now, probably why the researchers did this, made the molecule a little bit more rigid. So with that double bond, there's not as much flexibility in this molecule, and that may have changed the activity slightly. But this drug is on the market. It's Thioxanthene. So this drug is on the market with just that simple modification, and then also the structure-activity relationships and the mechanism of action of the Thioxanthenes are the same as for the phenothiazines. So please just make a note of that. If I do ask a question in the exams on the SARs of the Thioxanthenes, you can then provide the SARs that we've just learned about the phenothiazines, but then just make note that the only structural difference is now we have the double bond. That's probably now reduced some of the flexibility or decreased some of the flexibility of the drug. Then we also get the butyrophenones, and the prototype drug in this class is haloperidol. Haloperidol is something that is quite commonly used. Haloperidol is a dopamine D2 receptor antagonist. We know this because it's a typical antipsychotic, but it's a very potent D2 receptor antagonist, and it has a very high incidence of dopaminergic type side effects or Parkinsonian-like side effects. So it's related to its potency on the D2 receptor. Then if we look at the the structure of the butyrophenones, and if we look at the pharmacophore of the butyrophenones, it needs to have a 4-carbon spacer. Now, if you just go and count this spacer, you will see there's 1, 2, 3 carbons. But remember that carbon on the carbonyl also needs to be counted. So it's 1, 2, 3, 4 carbon spacer. If you change the number of carbons in the spacer, you lose the activity, the antipsychotic activity of the butyrophenones. There needs to be a tertiary amine, so you can already see a common theme here for the majority of the antipsychotics. Being a typical or atypical antipsychotic has a tertiary amine, and it seems as though that this is a common feature in all of the antipsychotics having this tertiary amine. That tertiary amine is also important for salt formation, to make the drugs in oral form and convert it into the salt of that drug to increase water solubility. This phenone, so the phenone basically means it's an aromatic group that's directly connected to a C double bond O, a carbonyl. So that phenone type structure is important, and it's part of the pharmacophore. And also a fluoro-substituted halogen in the para position of the phenone. Remember, that's para, that's ortho, that's metha, that's para position of the fluoro leads to optimal activity. So this is basically the pharmacophore of the butyrophenones. You need to know this pharmacophore. You need to be able to identify these groups and showcase the pharmacophoric groups within this structure. The main oxyphoric groups within this molecule is at this R2 position, and you'll see they've done quite a few ring chain transformations on this R2 position to increase or decrease the activity of this drug class. You can also go through my notes. I do discuss it quite in depth, the different structural properties. So similar to the antipsychotic, to the phenothiazines, they've also made water-soluble salts of the butyrophenones. It's the same principle. Use hydrochloric acid on that tertiary amine. You make the salt formation, make it more water-soluble, can be absorbed in the gastrointestinal tract. Once it's absorbed, it converts back to the parent drug, crosses the blood-brain barrier, effective in the central nervous system against psychosis. Also here, similar to the phenothiazines, they've also made intramuscular depot injections of the butyrophenones. I did discuss that in length of the phenothiazines, so I'm not going to go over it again. But for instance, with the haloperidol, what they've done, this is the parent structure. That compound needs to be used 3 times daily. They made a decanoate ester because on the Y position of haloperidol, there's a hydroxyl group. We know that if there's an hydroxyl group, you can react that hydroxyl group with a carboxylic acid to form a prodrug. And this is what they've done. They made a decanoate prodrug. You can see that is the ester that's now connected to the Y position. There's 8 carbons, increases the lipophilicity, making it a depot injection, inject it into the muscle, forms a bolus, and it's a slow release of the drug over time as the esterase enzymes converts it back into the parent drug. And you can see here again, the intramuscular depot injection only needs to take every 1 to 2 weeks for these patients. So it does assist with patient compliance. If we look at the structure-activity relationships, we need a parafluoro group. The lengthening or shortening of this chain that decreases the antipsychotic effects. We need this terminal nitrogen in here. That terminal nitrogen can be in this position, or it can be in any other position within this ring system. There needs to be an aromatic group that is connected to the 6-atom ring system. And that aromatic group can either be by one spacer or directly conjugated to the piperidine group. And then there's also a Y group for the butyrophenones that is also part of the oxophoric group, where that can change either into halogens or alcohols or whatever. And in the case for haloperidol, that Y group is an OH. So basically, you can do structural modifications on this Y position, on this aromatic position, and then this 6-membered ring, where the nitrogen can move into different positions in this 6-membered ring. So this is just some of the structure-activity relationships of the butyrophenones. Again, important, these structure-activity relationships, very important for the exam to write it down, or also be able to apply what you've learned here. Then we go to the atypical antipsychotics. Now you will note here the atypical antipsychotics, it's mainly the pharmacology thereof. Because these drugs are non-selective drugs, they work on various different targets at the same time, there's not much on the structure-activity relationships of these drugs. So the atypical antipsychotics, like I've previously said, they work on different receptors in the dopamine pathway. It can be serotonin, glutaminergic, or the D2 or D1 receptors as well. And because they work on all of these different targets at the same time, at the moderate dose, there is typically less EPS symptoms associated with the atypical antipsychotics, because these are modern drugs now. They've tried to improve on the properties of the older antipsychotics. So the first class of atypical antipsychotics is the benzodiazepines. You can go through this on your own time. You can have a look at its mechanism of action. I think the mechanism of action is what is important here for me, maybe as an MCQ question. You can also have a look at the structural properties. You can again see there's a tertiary amine. That's a common theme for these type of drugs. We need that tertiary amine. There's this X group here, and then we have the benzodiazepine heterocycle making up this 3 different ring systems. Within the benzodiazepines, we get structural variants or derivatives, like for instance, the benzoxazepines, the benzodiazepines, and the benzothiazepine, where that X position is then substituted with different functional moieties. Also, the piperazine substitution on that 11 position. So on this 11 position, there's a piperazine ring on this 11 position. And that piperazine ring is also then important for salt formation to make the drug more water soluble. So you can see continuous common theme where we have the tertiary nitrogen, where we have the piperazine or piperidine functional moieties, and where they can also do salt formation. So the same thing with the atypical antipsychotics, where they've used some of these strategies also to improve on the properties of these drugs. Just take note of these structural features. Maybe there could be an MCQ question on this. Here I've just shown you some general atypical benzodiazepine antipsychotics. Please just note the piperazine ring that we've just spoken about on that 11 position. You can see where it is substituted. It shows you quite nicely what these structures do look like. Like I said, there's not much structure-activity relationships on these drugs. They are non-selective atypical antipsychotics. Then we also get some other antipsychotic agents like the benzoxazoles and the benzisothiazoles like risperidone and ziprasidone. These 2 drug classes, and what I want you to do here is to be able to compare and distinguish between these 2 different drug classes or these 2 different drugs. You will see that they are atypical antipsychotics. They work on different receptors. You can see which structure is the benzoxazole, and in this case, you can also see where the benzoisothiazole is. What I would like to do here is maybe just draw up a table, have a look at these two drug classes, be able to answer a few questions in the exams, like for instance, MCQs, on its mechanism of action, and maybe also on its differences, the differences between ziprasidone and risperidone. So please just take note of this and be prepared for the exams. I think that brings me to the end of my lesson. If there are any questions, then please bring your questions to our next face-to-face session. Thank you, ladies and gentlemen.